All right, hello and welcome to the Calculus 1 Exam 2 review video for fall 2021. I'm going to go ahead and jump right into it. So for question 1, it says if f is a differentiable function that has a local maximum at x equals c, then which of the following is true? So because we have this local maximum, well, what have we used in the past to decide if something is a local max or min or some sort of extrema? We're using that first derivative, right? And specifically, when that first derivative is equal to 0, what values of x give the first derivative equal to 0, those are going to be our extrema. So that means that if f is differentiable, that means f prime of c is going to equal 0. So that's going to be our answer there. So because we know it has to equal 0, those first two options are going to be out. These last two options, so they're saying that f prime of c is either greater than or less than f prime of x for all x in the domain. And so what this is saying is either this is a maximum or a minimum, but not a max or min for the f function, it's for the f prime function. So since x equals c is a maximum on our function f, we don't want to use that to describe the derivative function. All right, on to question 2. We want to assume that g is twice differentiable, so that means we can take the derivative twice. And then it's on this closed interval from 1 to 5 and has exactly one critical point at x equals 2.5. So we want to identify the statements that, if true, would be a valid justification that g of 2.5 is an absolute maximum. So this keyword absolute here is different from a local maximum. So we want to remember that whenever we pick our options. All right, so first thing, if we have exactly one critical point at x equals 2.5, then typically, you would find that critical point by setting the derivative equal to 0, and you would solve for that x. So that means that if you had x equals 2.5 being a local maximum, then that derivative at that point would equal 0. But in this case, we want this g of 2.5 to be an absolute maximum. So that doesn't necessarily mean that at this critical point here that it's a local maximum. It could be one of those endpoints. So we don't want to consider any of the first derivatives because that doesn't necessarily have to be true. But we do need to know something about the second derivative. Because it's an absolute maximum, that means we're going to have some sort of downwards concavity. So concave down. And when it's concave down, that means that our second derivative is going to be less than 0, right? It's going to be negative. So our first option we want to pick here is a second derivative at that point is going to be less than 0 for that downwards concavity. And for that downwards concavity, we know that the derivative, so g prime, is going to be g in general is going to be increasing and then decreasing to form that sort of concavity. So that means that g prime is going to be positive and then to negative. So if we're around this point, x equals 2.5, then that means that, say, g prime of 1 is going to have a positive derivative, and then g prime of 3. So 1 is before 2.5 and it's going to be positive. Anything after 2.5 is going to be negative. So that means that this will also be one of our answers here. And then lastly, so we have just values of g. So we want g of 2.5 to be the absolute maximum. So that means that we can't have any values within this interval being greater than g of 2.5. So here, that's not what we want. And then here, we have that g of 2.5 as that maximum value, so this is another one of our answers. So we should have 3 overall. We have g double prime of 2.5 is going to be less than 0. Then we have g prime of 1 is greater than 0, and g prime of 3 is less than 0. And then finally, g of 1 is less than g of 5 is less than g of 2.5. So those are all valid justifications so that the g of 2.5 will be an absolute maximum on this interval. So on to question 3. So below we have this graph of the derivative of our function f. And we want to find where f of x has a maximum value. So like we've done in the past, we can find the critical points of a function by finding when its derivative equals 0. So what values of x does our derivative equal 0? So where does it cross the x-axis? Well, that's going to be at x equals -8, -4, +1, and +4. So overall, these are the only points that could possibly be our maximum, so we can take out any points. So this -1.5 is not going to be an option. And then, yeah, so the rest of these are looking okay. So now we just need to decide, well, are these critical points, are they maximums or minimums, or, well, you know, what can we figure out about them? So if we know that if it's a maximum, so if it's a maximum like this or a minimum like this, that derivative is going to be going from positive to negative, since we have that increase and then decrease of the actual function f. And then opposite for a minimum. So for a maximum, we want to see where f prime of x is going from positive then to negative around that critical point. So here we have negative and negative, so that's definitely not going to be one of our options. Here we have negative to positive, so this is actually going to be a minimum, so we're looking for a maximum. Here we go positive to negative, so that one's looking pretty good. And then again, negative to positive, so it looks like our final answer is just going to be x equals 1. All right, question 4. We have this differentiable function, and we want to solve for the specific derivative when x equals 3. All right, so here we have one function multiplied to another, so we know we're going to have to use product rule. So we're going to have x prime times f of x squared, and then plus, keep the x, and then f prime of x squared. All right, so let's just start by taking those derivatives. Derivative of x is just 1, so then we're going to be left with f of x squared plus keep our x. And then here we have to notice that because we have this x squared as our input, we're going to have a chain, so we're going to need to use chain rule here. So we'll keep the derivative of x squared, but then we need to multiply by the derivative of the inside, which is just going to be 2x. So we're going to be left with f of x squared plus, and I'll bring that 2x to the front, so we'll get 2x squared times f prime of x squared. So we need to remember to use that chain rule because our final answer will actually be very different if we don't have that. So now that we've taken the derivative in general, let's plug in our x equals 3. So we'll get f of 3 squared plus 2, 3 squared, f prime of 3 squared. So that's going to be f of 9 plus 2 times 9 times f prime of 9. And looking at our question, f prime of 9 is equal to 5. And then we have 18 f prime of 9 is going to be equal to 9. So our final answer should come out to, if you plug into your calculator, we'll get 167. There we go. All right, question 5. We have y equals sine of x over 4x, and we want to solve for the derivative at the point pi over 3. And we want to round our final answer to 3 decimal places. So we have one function divided by another, so we're going to need to use quotient rule. So let's go ahead and write that out. dy dx is going to be equal to the derivative of the first times the second minus the first times the derivative of the second, and then over the bottom squared. All right, so sine of x, the derivative of that's just going to be cosine of x, and we'll keep the 4x there, minus keep the sine x, take the derivative, that's just going to come out to 4, and then we'll get 16x squared on the bottom. All right, so now we want to take the derivative. We've done it just generally, but now let's find what it evaluates to at x equals pi over 3. So we're going to get cosine pi over 3 times 4 pi over 3 minus sine of pi over 3 times 4. And then on the bottom, we're going to get 16 over pi squared over 9. Cosine of pi over 3 is going to come out to 1/2. And it's going to be 4 pi over 3 still. Sine of pi over 3 is going to be square root of 3 over 2. Keep our 4. 16 pi squared over 9. We can simplify this a little bit more. We get 2 pi over 3 minus 2 square roots of 3 over 16 pi squared over 9. And then after plugging that into your calculator, especially because we have these pi's and the square root of 3 here, you should get something around negative 0.078, something along those lines. But that's it. On to question 6, so there's two parts here. We have this hot air balloon problem, and then we also have an area problem. So we have a related rates problem, which is this one here, and then a optimization problem on the next one. So for 6A, you can solve the actual balloon problem, or you can start with 6C and get partial credit. But the process for these is the same. The only difference is for 6A, you have to set up the problem in advance. So it's not actually too bad. So let's check out, I will go over both, but let's check out 6A first. So we have a hot air balloon rising straight up from the level field and is tracked by a rangefinder that's 500 feet from the liftoff point. So we know that this this side length is always going to be 500 no matter where that balloon is. At the moment, the rangefinder's elevation angle is pi over 4, so when theta equals pi over 4, the angle is increasing at a rate of 0.41 radians per minute. So that means that our angle, our angle is increasing, so d theta dt when our angle is pi over 4 is going to be equal to 0.14 radians per minute. So because this is a related rates problem, we most definitely will be using that number here. And so we want to know how fast is the balloon rising at that moment. So we have this height here, and we're solving for dh dt. So we need to find some formula that we can relate height with the angle. And what's one way we can do that? Using trig. So, well, we have two side lengths. So tangent of theta is going to give us that opposite over adjacent. So our h over our adjacent, which is 500. And we want to take the derivative of both sides with respect to t. All right, so tangent theta is going to give us secant squared theta, and then we want to multiply by our d theta dt. And then similarly, h over 500 is just going to give us 1 over 500 dh dt. And so we know our angle, and we know our d theta dt at this angle, so we just want to solve for that height. So dh dt is going to be equal to 500 secant squared of pi over 4 times our d theta dt, which is 0.14. And plugging that into your calculator, we should get 140. So it's going to be 140, and then I believe this is in feet, so feet per minute. So after setting it up, not too bad to solve. However, if you weren't sure how to set it up using trig, part 6C does give us the option of not having to set it up, but just solving the related rates problem. So let's go over that part now. So here, we want to pretend that theta is related to h using this h squared minus natural log of theta equation. So we're still going to use this theta equals pi over 4, and d theta dt is going to be 0.14 radians per minute. But here we don't have to actually set up the equation to actually relate the problem. Here we just have a different equation, and we're just using those numbers. So we're still going to take the derivative with respect to t on both sides. So it's going to leave us with 2h dh dt. Natural log of theta is going to give us 1 over theta, and then d theta dt. And we're still going to solve for dh dt. So we're going to get this 1 over dividing by 2h. We'll get 1 over 2h theta d theta dt. And so one step that we have to take on this problem that we didn't have to do on the last one is actually solving for what h is when theta equals pi over 4. Because our derivative here, we ended up just getting a constant term, we didn't actually have to solve that, but here we do. So after this side, so we have this triangle here, we know this is 500, and here we have this pi over 4. So we're still going to have to use tangent to solve for what that h is. So h is going to be equal to 500 tangent of pi over 4, right? Because tangent of theta is going to be equal to opposite over adjacent. So plugging that in, we're going to get 1 over 2, and then 500 tangent of pi over 4 times our theta, which is pi over 4. So let me extend that. And then our d theta dt is still the same, and that's going to come out to 0.14. So plugging that into your calculator, you'll get dh dt is going to be about 0.0000178. So a much smaller number than what we had before. And 6c does tell us that this isn't the actual solution to the problem, but it does keep us from having to solve for that correct relationship. However, in this problem, we did have to use that tangent anyway to relate that angle to our h. So, you were kind of solving through using tangent anyway, so being able to recognize that, well, if you take the derivative of both sides of that tangent equation, you can actually relate the rates as well. So there's a similar process for both problems, so it's just a matter of what you feel most comfortable setting up. On to the last problem of the review. So we have 6b, and there's also 6d that I will also go over, but let's start with 6b real quick. So we have a company that wants to fence a rectangular storage area consisting of 3 separate compartments of equal size. The fencing costs $2 per linear foot, and the company has a budget of $160 for building the storage area. We want to find the length and width of the storage area that maximizes the total area. So we are working with 2 things here. We have area, and then we also have the amount of fencing, or how I'm going to write it is in the cost of fencing. So the cost of fencing with respect to the length and the width of this section here. So we know our area is going to be equal to our length times our width. Then the cost of fencing, so because we want to maximize the total area, we also want to maximize the amount of fencing that we use with that area. So the maximum cost we can use is $160 total. And then it's $2 per linear foot. So we have one side length L here, one side length L here. So we have 2, so it's $2 times, well, we have 2L. So 2L, this is the amount of feet, and then times $2 for that amount. And then we're also going to add 2 times, we have 1, 2, 3, 4 W's here. So I'm going to go ahead and simplify this a little bit and divide out 2. So we're going to get 80 equals 2L plus 4W. And then dividing by 2 one more time, we'll get 40 is equal to L plus 2W. So because this is an optimization problem, we want to take this one here and plug it into that one so that we have area just in terms of one variable, so we can take that derivative a little bit easier. So we can rewrite this as the length is equal to 40 minus 2W. Plugging that into our area equation, we get area is equal to 40 minus 2W times W, which is the same as 40W minus 2W squared. All right, now let's take the derivative of both sides. So A prime is going to be equal to 40 minus 4W. And then to optimize it, we want to find the maximum value there, or maximum, minimum, something like that. So we'll do that by setting the derivative equal to 0, just like we would for solving for critical points of a function. All right, so we'll get 40 is equal to 4W, and then divide by 4, we'll get our width is 10, and that's going to be 10, I believe, feet, yeah. So now that we have our width, we can solve for our length, since we had this here. So our length is going to be equal to 40 minus 2 times 10, which is going to come out to 20 feet. So find the length and width of the storage area that maximizes the area. So that's going to be width is equal to 10 feet, length is equal to 20 feet. There's that. Now, just like on the previous problem, if you're not sure how to set up the problem, there is this other 6D option that gives you the equations to use. You still optimize them the same way, but we're kind of skipping the step of actually setting up the problem that actually relates the variables to each other in the correct way. So here we have an area equation, and it's already in terms of one variable. So if we find the maximum W that maximizes area, then we can use that to solve for the length here. So we'll take our area equation and take the derivative of both sides. So we get A prime. I'm going to go ahead and multiply this out. So we're going to get W squared plus 6W plus 900 plus 100. So taking the derivative of that, we're going to be left with 2w plus 6. And then to maximize it, we just want to set that equal to 0. So solving for w, we'll get 2w is equal to negative 6, which gives us w is negative 3. So as you can see here, this is saying that we have a negative length. So obviously this equation is not accurate to the problem. We can solve for a number, but in context it doesn't totally make sense. But I'm going to go ahead and solve for L anyway. So we have this L is equal to 2w minus 5. So we'll get 2 times negative 3 minus 5, which is negative 6 minus 5. So our L is going to be negative 11 feet. So again, in context, these numbers don't completely make sense. We can't have a negative length. But in terms of approaching the problem and solving for those maximums and minimum values, those critical points there, optimizing that equation, we do get a value. And these two values are related to each other. So skipping the step of having to set it up and using this 6D problem, it's a little different in context, but the actual process of optimizing is about the same. Finding that derivative, setting it equal to 0, and then solving for that maximum value. So there we go. We hope that this video has helped out a little bit in your review, and if you made it this far, good luck. Try out some of those other problems again, and good luck on your exam.